So now we're going to conclude our look at section 2.4 with both finding all the real zeros and using the zeros to work backwards and find the polynomial. So first we'll look at how to work backwards. Instead of giving you the polynomial and asking you to factor it down and find the zeros that work, now they're going to give you the list of zeros and ask you to multiply the factors together so that you can find what the original polynomial would have been. So a lot of this is going to come to writing each solution in factor form. So if they say 3 is a solution, then you would write x minus 3 as a factor. And you do that for every single one they give you, and you'll be distributing those answers. Now, some of the extra information they might give you to affect the polynomial would be the degree, which is the biggest exponent you should have. So they might say like degree 3, which means your first term should have an x cubed in it. If they say degree 4, then your first term should have an x to the 4th power in it. They may also give you a leading coefficient. So if they say the leading coefficient is a 2, then that just means you will need to multiply one of your factors through by a 2, and that will take care of that part. The biggest trick with the degree is maybe they give you 3 solutions, but they say it should be degree 4. Then you might need to put an exponent on one of the factors to affect the multiplicity of it at that point. So here's a quick example to describe working backwards. The first piece of information I'm going to use is actually the zeros here. So if negative 4 is a solution, then that means I have x plus 4 as a factor. For 1 as a solution, I have x minus 1 as a factor. And for 5 as a solution, that means I have x minus 5 as a factor. So the idea is if I multiply these together, I would get a polynomial. Now, they want to be a little more specific with this because they want this to come out to a degree of 3 and a coefficient of 2. So I'm just going to start distributing this expression out. It doesn't really matter which 2 factors you multiply together first. So in this case, I think I'm going to multiply the x minus 1 times x minus 5. So I'm going to leave x plus 4 alone for a second. And then if I just focus on this part and I FOIL or distribute, I'll have x times x. And then for the outside and inside product, you'll have minus 5x and minus 1x. So I'm just going to go ahead and combine those to get negative 6x. And for the last product, that would be a plus 5. So you only want to multiply 2 factors together at a time. So now I'm going to take this binomial and multiply it by this trinomial. So again, I need to distribute x times x squared, x times negative 6x, x times 5. So now for this first term in the binomial, I've multiplied it by all 3 of these. So now to continue distributing, I'm going to come to the second term in the binomial and multiply it by all 3 of these. So now I have 4 times x squared, 4 times negative 6x, and 4 times 5. There are some like terms here that I can combine. The x cubed stays as it is. For my x squareds, I have a negative 6 and a positive 4, so this will be negative 2x squared. 5x minus 24x is negative 19. And then a plus 20 that stays as it is. So now let's compare to the other information they gave me. They said that it should have a leading coefficient of 2 and a degree of 3. Well, the degree of 3 is fine because my polynomial here is starting with the 3rd power, and that's what the degree refers to. What is the biggest exponent you see in the variable? So I don't need to do anything for this. If they had said degree of 4, then it didn't really specify which one I would need to do it to, but it means that I would need to affect the multiplicity of one of these. So for one of them, I would put it at the 2nd power, and then that way when I did all my distributing out, I would have ended up with x to the 4th power instead of x to the 3rd. Now for the leading coefficient of 2, my leading coefficient is a 1. So what I need to do here to change that is figure out what to multiply the whole polynomial by so that the first term comes out to the indicated number. In this case, it just means I need to multiply everything by 2. So if I distribute that through, I'm going to double all of the coefficients and end up with something that looks like this. So this is just straight up working backwards from what we've been doing. Usually I would give you this polynomial. In fact, it would be good practice for you to take that polynomial and see if you can factor it down using synthetic division and a list of possible roots, etc. So once you work this all the way down, you would have found those three solutions, and that would have been your list of zeros for the polynomial. This last concept, this fundamental theorem of algebra, this is actually just a handy tool to help you with what we were doing in the earlier sections of 2.4. So the idea is that you look at the degree of your polynomial. If the biggest exponent you see for the x's is 4, for example, then you should expect there to be 4 roots. So this is basically just a nice way of letting you know how many answers to expect, which is also useful as far as you being able to say, yes, I found them all, or no, I'm still missing one, I need to find another one because I don't have all my answers yet. So right here, for example, my biggest exponent is a 4. So I know that if I go through the process of listing the possible roots and then testing them with synthetic division, I know that at the end, I should end up with 4 different answers. The number of answers or solutions you should expect is the same as the number that you have for the biggest exponent. I do want to caution you that this includes the multiplicity of the roots. So since this exponent is a 4, I might only have 3 different numbers, like x plus 2, x minus 1, and x plus 3, but one of them might have a power on it to compensate for that. So when you have a multiplicity of 2, that does count as 2 of the different roots, even though it's just one root being repeated. So do consider the multiplicity. It may be an exponent of 4. You may only see 3 answers, but if one of them has the second power, that means you do have 4 actually. So here's a quick example. We're going to be doing more of the same thing. I'm just going to be commenting on how now I expect there to be 3 answers. Also, these questions are going to start to get a little trickier because now you're going to find that I'm giving you some that you can't factor, which means you'll have to resort to using the quadratic formula to find a couple of the answers. But to start off here, my list of possible roots, just like we were doing in the last section, this is the plus or minus numbers, and it's the factors of the constant, so 1 and 3, over the factors of the first number, which in this case is 1, so it's not going to affect anything. So I just have to worry about the numbers 1, -1, 3, and -3. Now don't forget how some of the earlier concepts I told you can be applied to this one. I showed you guys that in addition to using synthetic division to find the remainder, you could also just plug one of the numbers directly into the polynomial. And that can be handy as just a way of quickly identifying whether a number will be a solution or not. For example, I don't think 1 is going to work, because if I plugged that in for the x values, I would have 1 plus 7 plus 11 minus 3. And that's not going to equal 0. It doesn't sound very close to 0. So I'm just not even going to bother using synthetic division with a 1. You can do the same thing with any of the numbers, but usually the ones and the negative ones are the easiest ones to check. So let's try synthetic division with -1 instead. So again, you can test this answer ahead of time by plugging it directly in for x, but even if it does end up equaling 0, you still have to go through the synthetic division process because we need the numbers that come from underneath the synthetic division. So the first number comes down, then I multiply, add, multiply, add, multiply, and add. And that one didn't work either. So I tried the next number. Now again, I don't think 3 is a good choice because if I plug 3 into these, I'm going to end up with a huge number because these are all positive. So instead, I'm going to try the -3 answer. Coefficients are still 1, 7, 11, and -3. First number comes down, multiply, add, multiply, add, and multiply, add. Now that one did work, which means I now have the polynomial breakdown as x plus 3. If the solution was -3, then the factor is x plus 3. And then what was left is 1x squared plus 4x minus 1. So here's another twist. Here's where the problem is getting a little more difficult than the other ones we did. This cannot be factored. So to get my last answers, I'm going to have to use the quadratic formula on that part. So -b plus or minus square root of b squared, which in this case is going to be 16, minus 4 times a times c. And all of this gets divided by 2 times a. So in this case, 2 times 1. If I simplify this a little bit, I'll have negative 4 plus or minus the square root of negative 4 times 1 times negative 1 is positive 4, and 16 plus 4 is 20. We've talked about simplifying radicals earlier in the class. So square root of 20, you can break this down as 2 root 5 Don't forget the process of simplifying radicals. And then since all of these numbers are divisible by 2, I can actually cancel a 2 out from all of them or reduce it all by 2. So then this will be negative 2 plus or minus the square root of 5. So that's 2 answers here. And then I got 1 answer that I determined from synthetic division, the negative 3 solution. So altogether, I have 3 answers. Since the biggest exponent was a 3, that means I have all of my answers. So I can now state that the solutions are negative 3, and then the negative 2 plus or minus root 5. Those would be my real zeros. Now these are real zeros because I didn't get an imaginary answer out of that, but that's a hint of things to come. We will start doing imaginary or complex zeros in the next section. So that's all I'm going to cover in this video for today. You will notice that on the PowerPoint I provided for you guys, I did have another example, but I think I'm going to work that one out with you guys in class. It does take a little bit of time, and I want to make sure you guys can ask me questions as I'm working through this one. So there was one more example in the PowerPoint, and we'll talk about that one in class. So that's all for the notes now. Thank you guys.